Dear students, let's understand using this presentation that how to draw resonating structures of benzene derivatives. Benzene derivatives means the compounds in which benzene has some substituent on it like OH, NO2, CHO, COH, etc. So they become benzene derivatives because they have been derived from benzene. So let's get started and practice drawing resonating structures. I have kept the framework ready here so that we can quickly draw the resonating structures of benzene derivatives. Let us start with benzene having OH on it. Now, in this compound, which is called phenol, we all know this is phenol and this is used in IUPAC nomenclature as it is. The OH group, which is attached, the oxygen of this OH group has lone pairs on it, electron rich. So what will happen when I draw the structures? These lone pairs, they can be shifted towards benzene. So this group becomes electron donating group. So the first slide having these structures will be used to explain that if there is an electron donating group attached to benzene, how to draw the resonating structures for it. So let's start. I'll just remove it from here to avoid any confusions. Now, we show that the lone pair is shifting between oxygen and this carbon of benzene to make a double bond here. In this process, this carbon, which is going to make a double bond with oxygen of OH group, is going to have 5 bonds. Once it gets a double bond here also, there will be 5 bonds, which is not possible. So simultaneously, this pi bond will break and the electron density will shift on the carbon where the double bond is ending. So this is how we show the arrows. Do it slowly in the beginning. And once you have the clarity of concept, you will be able to do it faster. OH, the double bond is with oxygen, and in the process oxygen is getting a positive charge because the lone pair is not to oxygen only, not belonging to oxygen only. The lone pair has shifted to give rise to a double bond between carbon and oxygen because the electron density is shifting away from belonging to only oxygen to being shared between carbon and oxygen. That's why there is a positive charge. These two bonds are as it is. We have not touched them yet. And here I told you the electrons will shift. See the arrow. I have shown the tail of the arrow where the pi electrons are and the head of the arrow where the electron density is finally shifting. So it is shifting on this carbon. That's why my arrow head is here. So when it shifts here, I'll get a negative charge. Now see the first two structures. In the first one, there was no charge. It was neutral. Now when I have a positive charge somewhere, it is mandatory that I'll get a negative charge somewhere because overall the molecule is neutral. Now, I will show the movement. Now, this negative charge, that means excess of electrons, they will not be localized here. It will move between this carbon and the next carbon. See the head of the arrow between these two carbons because now it will give me a double bond here. So when that happens, this carbon is already having hydrogen, right? And I'm going to get a double bond here. So this bond will break and simultaneously you will show this pi electron density will shift on the carbon where the double bond is ending. This will remain as it is till the end. I'm using different colors just to explain it. You don't have to use different colors. Understand the concept and draw it. This is not touched yet. Here I am getting a double bond because of the shifting of electron from negative charge to pi bond making, and here the electron density has come on this carbon. Now The negative charge will shift between the carbon where the negative charge is and the next carbon. That means I'll get a double bond here, and simultaneously this double bond will break and the negative charge will come on this carbon where the double bond is ending. This is as it is. I have a double bond. I have oxygen and hydrogen here, and you have a positive charge which is still maintained because we are showing structures that how the electron density is moving throughout the benzene. I'll get a double bond here and you get a negative charge here. Once I get this, finally, this will shift between the carbon where the negative charge is and the next carbon, and this will finally go back here. So I am going to get this double bond here. This I got. Now I have got this double bond here. This is again converted to a single bond, and OH is here. Now see carefully. If you see the first structure and the last structure, I mean this and this, there is only one difference. See the difference. The difference is only in the placement of these pi bonds. They are still alternate, but here the bond was between, suppose, this and this carbon. Now between this and this carbon there is no double bond. It has shifted, it has moved, but the aromatic character of the compound is still maintained. It is still intact. So what are we trying to show using these structures? We are showing that if there is a group attached to benzene, it is going to show the different kind of resonating structures, and in the resonating structures you would notice the negative charge. If it is electron donating group like OH, generally the abbreviation EDG is used, but I don't recommend such abbreviations. When you write any answer, you write the full thing. So electron donating group like OH, when they are present on benzene, you can see the negative charge is coming at ortho, para, and this is also ortho. So if anything which has electron deficiency, we call that electrophile. If any electrophile is coming and attacking on phenol, it's very clear that electron density is concentrated at ortho and para. So that electrophile will come and attack at ortho and para. This is how we justify that if phenol reacts with something which is giving rise to electrophile, I mean to say if phenol is undergoing electrophilic substitution reaction, then why only ortho and para products are obtained? Because the electron density is concentrated at ortho and para. Why so? Because OH is there. And when OH is shifting its electrons, uh, using a resonance concept, we can explain it. When it is moving its electrons towards benzene, how the electrons are moving and how the electron density is being concentrated at ortho and para makes it very clear. Now, let's make one more. I have benzene, and on benzene, I am going to now put NH2 as a substituent. So this becomes benzene derivative, which we call aniline or aminobenzene. Now we have to first decide whether this NH2 group is electron donating or withdrawing, and then we start making the structure. So this is the name of the compound. Nitrogen has a lone pair on it. Okay. Now the lone pair is on this nitrogen, then there is a single bond, and then you have a double bond. So whenever you have alternate double bonds, or whenever you have positive charge or negative charge or lone pair and then alternate double bond, there will always be resonance. So these electrons in the lone pair, they cannot shift towards hydrogen because hydrogen can never make a double bond. So where would they go? They are going to come towards benzene only. So that's how this group also becomes electron donating group. Now we are drawing the resonating structures using this NH2, which is electron donating group, and let us see what structures we get and how it is going to explain that why electrophile attacks on specific positions only when there is already a substituent on benzene. So here I have a lone pair on nitrogen. See, in the same manner as we did for phenol, I'm going to shift the electrons here. So I'll show the electron pair is coming between nitrogen and carbon. Simultaneously, this is shifting on the carbon where double bond is ending. So to start with, these are as it is. Here it will convert to a negative charge. And this is converted to a double bond temporarily. Because in the last structure, you will see that again we have the carbon attached with a single bond to nitrogen of NH2. And here I am getting a positive charge. This is the positive charge. Now, this will come between the carbon where the negative charge is and the next carbon, and simultaneously this double bond will break and we will go to the carbon where the double bond is ending. So we have not yet touched this bond. This is as it is. Here we got a double bond. Here we got a negative charge, para position, and you have double bond with NH2 and nitrogen is having a positive charge on it. Again, this will move like this, and here this will come to the carbon where the double bond is ending. Now you can quickly show that this remains as NH2 positive till the end, and I have got a double bond here, alternate double bond here, and a negative charge here. Now we have come to the last structure. This will come between the carbon where it is the negative charge and the next carbon, and this will go back to nitrogen. So the complete delocalization of pi electrons is taking place, which is responsible for the aromatic character, hence stability of these compounds. So I have got again single bond NH2, and see the placement of double bonds here and here. Still alternate, but it is different. Now here again, we can emphasize on the same point that the negative charge is coming at ortho, para, ortho. Both ortho positions and para positions are having high electron density. So if any electrophile comes, which is in the need of electrons, it will definitely attack at ortho and para. But suppose a nucleophile comes, any nucleophile which is electron rich, so it will attack at meta because at one carbon NH2 is there. At three carbons, ortho and para, electron density is high. So they will repel this nucleophile. So only meta is left. This is how we explain it. Let's take another group now. I am taking NO2 group here. N double bond O and single bond O, which is a coordinate bond. You can show it like this or like a coordinate bond. Now this is the substituent on benzene, and you can see that the carbon which is attached to nitrogen, we have to decide whether the group is electron donating towards benzene or it is electron withdrawing. It will withdraw electrons towards itself. So for that you have to see the atom which is attached to carbon of benzene, and further it is attached to which particular atom with a double bond. So this is nitrogen which is attached to carbon here and oxygen with a double bond here. So oxygen being more electronegative will definitely try to attract electron density on itself, and in that process benzene will start shifting the electrons like this towards nitrogen, right? So this group becomes electron withdrawing group if it is attached to benzene like this. So once we decide that it is electron withdrawing group, then we can draw the resonating structures easily. So let's do that. So we are showing that nitrogen and oxygen double bond is converting into a single bond because oxygen being more electronegative is taking away electron density. So this nitrogen will be left with three bonds, right? So this carbon will be immediately shifting its electrons between carbon and nitrogen to give rise to a double bond here. This carbon is not losing anything because this carbon was making a double bond at this side. Now it will make a double bond with the nitrogen. So this carbon is going to have 4 bonds as earlier. So it's not losing anything. It's making bond with nitrogen. I'll just show it properly here, this nitrogen. Yes. So carbon has a double bond with this nitrogen. Single bond is as it is. We are not showing structures using this because there is already a double bond on this side which will take part in resonance quickly, right? So this is converting into single bond O, and now this oxygen will get a negative charge because the electron density from between nitrogen and oxygen has shifted on this oxygen, and these two double bonds we have not touched yet, but this particular carbon is at loss. Why? Because in this pi bond, one electron belongs to this carbon. This carbon which is bonded to nitrogen is again having 4 bonds, but the carbon which is here has lost one bond. Because of that, it becomes electron deficient and you get a positive charge on this carbon. Now this positive charge will attract electron density from here. This carbon, which is making a double bond with this carbon, will shift it on the other side where positive charge is. So this you will show the arrow from here to here, just that. That means the carbon which is here is making bond on the other side, the double bond. So I will be getting, this will remain as it is till the end. Nitrogen, single bond, oxygen with a negative charge, and you have a single bond here as it is. This is not yet touched. This has shifted the electrons, so I get a double bond here, but this carbon has lost its electron in the process, so this is getting a positive charge. Then this carbon is having a double bond with this carbon, so this is going to shift here now because there is a positive charge which is attracting electron density towards itself. That's how the movement is taking place. That's how resonance happens. So we are showing nitrogen here, oxygen with a negative charge as it is. This is single bond O. You can show just single bond or coordinate bond with an arrow. And you have this double bond now. This double bond will come here and this will get a positive charge. Simple. Then finally, because this carbon is in the need of electrons now, so this double bond will shift back here between this carbon and the carbon attached to NO2 group. And in the process, this oxygen will shift the electrons here back to get a double bond. So we are getting this double bond and this alternate double bonds, single bond, nitrogen, oxygen with a double bond with a nitrogen, and single bond oxygen. Again, the same thing I would say. If you compare the first resonating structure with the fifth resonating structure, you will see the position of alternate double bonds has changed. So resonating structures give you a clear idea that how the electron density moves throughout the benzene, taking into consideration electron donating or withdrawing group. And here you will notice that the positive charge, because electron withdrawing group is there, so benzene is going to develop positive charges. You have a positive charge at ortho, para, and again ortho. That means if any electrophile, suppose Cl plus is coming and attacking, so that will attack on meta position because at ortho and para there is already electron deficiency, positive charge. So electrophile will not get anything there. So see, benzene is called electron rich molecule always. So benzene derivatives are also electron rich because benzene has 3 pi bonds, 6 pi electrons. So it is electron rich. But we are saying at one carbon NO2 is there. So here the electrophile cannot come. And ortho and para positions, three more positions are having a positive charge. So where has the electron density of this electron rich species gone? So that must be on meta position, right? That is why when you have electron withdrawing group attached to benzene, the electrophile during electrophilic substitution reactions is going to attack at meta position. This is going to be very helpful when you actually give reasoning for such questions, when you explain the reason, and when you have to do the conversions. Now, next, let us take CHO. So this compound is, the earlier one was, and the previous slide was nitrobenzene. Here you have this aldehyde group. So this becomes benzaldehyde. This compound is benzaldehyde. So we are going to draw now resonating structures of benzaldehyde. In benzaldehyde, if you see the CHO group carefully, first you should know how to decide, as I am telling you again and again, how to decide the group is electron donating or withdrawing, and then we get started. So here again you have to see the atom which is attached to carbon of benzene. It is this carbon which is attached to hydrogen on one side. Hydrogen can never be involved in resonance. It can never make a double bond. So here the resonance will be on the right side only. I mean to say the resonance will start because of the action of electrons being shifted on oxygen, because oxygen is more electronegative. So this group also becomes electron withdrawing group. So as we had drawn the resonating structures in the previous slide using NO2, same way we are going to do it here. So I'll just remove this and let us start the resonating structures. So this has shifted here. Simultaneously, this electron density will shift between the carbon of benzene to which CHO is attached and the carbon of CHO, and these two are as it is. Here you get a positive charge because the pi electrons are shifting here to give rise to a double bond. Carbon, H as it is with a single bond, and you have oxygen with a negative charge now. Show the negative charge here. Next, electrons will be drifted this side because pi electrons are available and the adjacent carbon has electron deficiency. So this will be as it is. CHO with a negative charge, and you have this double bond as it is. This double bond has come, and this carbon, which is para position to CHO, is developing a positive charge. Next, this will shift here. Because of that, you have got a positive charge on this ortho position now, and this is still as it is. See, the more you practice drawing of such structures, the more efficient you would be. Practice is the key for everything. CHO. Okay. And in the end, I will show that this double bond is shifting here between this carbon and the carbon having a positive charge, and simultaneously this negative charge density will shift here between this carbon and oxygen to give rise to a double bond. So here I got a double bond, here, and I have got CHO back. C double bond OH. So this is how we draw the resonating structures, but first of all, we should be able to decide whether the group attached is electron donating or withdrawing. Now you can see again the electron density is less at ortho and para because they have developed positive charge. So when any electrophile comes which is electron seeking, it has only meta option left, so meta pe attack hoga. And if any nucleophile comes which is nucleus seeking, that will definitely attack at ortho and para positions. But Benzene is electron rich molecule, as I told you. So the electrophilic substitution reactions are more likely. Nucleophilic substitution takes place, but that will be less likely as compared to electrophilic substitution. Since we have drawn the resonating structures of electron donating and withdrawing groups, let's understand this concept quickly. That what does it mean by directive influence of a functional group in mono-substituted benzene? Mono-substituted, mono means one. So when there is only one substituent on benzene like OH you can see here, this was the first compound we started with for making the resonating structures. So when you draw the resonating structures, you will see that negative charge is coming at ortho, para, ortho. I'm repeating the same thing so that it is permanent in your mind and you can relate it properly. You can give the reasoning properly for the reasoning questions. So here what is happening? Electron donating group is here. Benzene is already electron rich. It has three pi bonds. And the group is again electron donating, which is making electron rich benzene more rich. How? You can see that on one carbon out of six carbons in benzene, on one carbon OH is attached itself, and the remaining five carbons, out of remaining five, three carbons are developing a negative charge on them. So that's why it becomes electron rich, because the negative charge electron density is concentrated at three positions. So such groups which are electron donating, they are also called activating groups. Why? Because they activate benzene ring more towards electrophilic substitution reactions. If any electrophile comes, it knows exactly where to attack. It will attack at ortho and para only. It will never go to meta if there is electron donating group like OH or NH2 attached to benzene. So that's why electron donating groups are called ortho and para directing groups. For what? For the incoming electrophile. They will direct the incoming electrophile at ortho and para positions. And same way, if you have group like NO2, in this presentation, we have drawn the resonating structures of NO2 also. Now, NO2 is electron withdrawing group. If there is any electron withdrawing group, that is also called deactivating group, because out of five remaining carbons, on one carbon NO2 is there, mono substitution is there, remaining five carbons, three carbons are developing a positive charge because the NO2 group is taking away electron density towards itself. So because of that, what happens? The benzene becomes electron deficient. Three carbons out of remaining five are developing a positive charge on them. So such groups are called deactivating groups. And meta-directing, because the electrophile can never attack at ortho and para. In such cases, there is already positive electron, positive charge, I should say, concentrated. So it will attack at meta positions, because at meta positions there is no positive charge. So there must be electron density, right? And these are the other examples apart from NO2, cyanide, CHO. We have drawn CHO also today. COR, acyl group, carboxylic group, ester group, SO3H. They all are deactivating groups because they all are electron withdrawing groups. And as I told you how to decide, you have to see the atom which is attached to carbon of benzene. Here nitrogen is attached, and further it is attached to oxygen, which is more electronegative. So it will become electron withdrawing group. If you have two hydrogens here, like in NH2, then hydrogens can never take electron density. They can never make a double bond. So that group remains electron donating group. So once you decide whether the group is electron donating or withdrawing, and then you draw the resonating structures, as many as you draw, it will give you more practice and you'll be very efficient in that. So that's all about this presentation. I hope it helps you. Thank you.